these newsletters, we have a lot of information about activities such as today, ongoing research activities, as well as publications from outside of the network, such as colleagues around the world who are also looking at PFAS. So we put a lot of updated information about really what's going on in the realm of research related to PFAS. And finally, I just want to acknowledge all of our collaborators and PIs. So the PIs from all of our state institutions, university institutions, are represented here with the pictures. The green boxes here, if you will, are participants today in the panel discussion. So I thank May Sun, Martin Barlaz, and Jeffrey Warren from the North Carolina Policy Collaboratory for being here today. And also, I want to thank again Jane Hoppin and her team at NC State, Kathleen Gray at UNC, and Jory Weintraub at Duke. They're our communications team, and they've done a great job getting us all organized to have an event like today. And then finally, and really importantly, I really want to thank our state collaborators at DEQ and the Department of Human Health Services. They've been so supportive of our research activities and have even provided experts from their teams to help us on various research things that we're doing in the network. And then finally, I also want to thank our federal collaborators at the US EPA and the National Institute of Environmental Health Sciences. So I hope you all enjoy today's event, and really thank you all for participating. And if you have any questions, feel free to reach out at any time. Thanks again.
Great, thank you so much for the introduction, Jason. I would now like to introduce Gary Sanders. He is the Stationary Source Compliance Branch Supervisor for the North Carolina Department of Air Quality. Gary has been working for the Department of Environmental Quality for over 20 years and has extensive experience in air and energy related issues and regulations, permitting, and emissions testing. I'll let you take it away now, Gary.
Okay, good morning. Thank you very much. So I'm going to give a brief overview of where we've come from the Division of Air Quality standpoint. As we all know, that here in North Carolina, part of this issue that we're dealing with, started back for most of us in 2017. And I got involved in October 2017 when it became more and more obvious that the PFAS contamination that we were seeing around the Chemours plant down below Fayetteville was actually an air emission related situation, as opposed to being releases to the plant groundwater underneath of the plant. So the overview was we quickly got on to figuring out how much PFAS was coming out and trying to get a hold of the chemistry for that particular facility. That facility is primarily a perfluorinated vinyl ethers plant, although it makes a few other products. So starting in October 2017, we began the process working with Chemours and EPA on developing test methods and also ultimately looking at how to reduce the contamination of the groundwater by reducing the release of the various PFAS into the air from the processes. So beginning in 2018, we had Chemours install carbon adsorption units on certain processes that were located in the facility. They're known as the vinyl ethers north area and the polymer processing aid area. And we've found a fairly significant decrease in emissions at that particular time from those sources were more fugitive in nature. The facility had some controls already installed, and unfortunately, it's fairly complicated, but they thought that they were emitting about 3.3 pounds per year. And when we actually got through all the testing, we discovered that it was more like 2,300 pounds per year of materials. To make a very long story and complicated story short, ultimately, we required by consent decree and then by a permit that the facility control emissions by 99.99% from a baseline level, which we work to establish through all the source testing. And so that's what most of the work has focused on in the last year or so. Chemours finished, they started constructing their thermal oxidizer on site approximately in May of 2019, and they did their initial performance test on the thermal oxidizer to check it out to make sure that it was operational at the end of 2019. The actual performance test was conducted in February of 2019. I'm going to share just one very brief photo of that particular device. So if you'll hang on while I tell it to share my screen and go there. And go to full screen, and there you should see it. So this is the thermal oxidizer that's been installed. It's been tested. We can test for at this particular time to control 99.99% of the emissions that are coming from the various processes. It's fairly tall, and the scrubber section is located along this particular southeast side. Basically, the thermal oxidizer takes the PFAS, turns it into hydrofluoric acid, where it's then recovered, and ultimately in another portion of the plant, it's reacted with calcium hydroxide to form calcium fluoride, which is then sent off-site to landfill. So we are beginning to see trends in the deposition sampling that has been done around the facility. There are still some unexplained spikes that we occasionally see, but we are beginning to see a downward trend. We began to see that last year, and that seems to continue. So that's the basic approach, overall perspective in terms of DAQ. From the standpoint at DEQ, in order to get a handle on the groundwater contamination and to stop adding this material to the loading that we has successfully and will continue to successfully decrease the amount of material added to the groundwater and ultimately to the Cape Fear River. So I'm going to leave it at that and make myself available for questions.
Thanks, Gary. Now we're going to move on to a presentation from Jeffrey Warren. Dr. Jeff Warren is the Executive Director of the NC Policy Collaboratory. Jeff was formerly trained as a marine geologist and has spent the past 15 years in state-level science policy positions. I'll turn it over to you now, Jeff.
Hey, am I off mute?
Yes, we can hear you.
My Zoom window just went away. Can you see my screen?
Yes, we can see your slides.
Okay, great. I have no idea where Zoom went. Thanks for everybody for joining us. I'm going to give a really quick overview on where we are. Dr. Surratt also already mentioned some of this. Dr. Surratt mentioned that we had some report deadline bumps. So the initial report was December 1, and that was the original appropriations legislation and study mandate. That was changed to October 15th last year. And then COVID really just stopped, as everybody knows, all of our lab work and specifically really derailed our water testing program. So we requested and received another 6-month bump. And our labs are up and running. Happy to hear that. But now the final report is due April 15th of next year. To give you a funding update, you'll remember the first appropriation was $5.13 million, and the collaboratory was challenged to utilize any other funds, including its challenge grant, to supplement and pull in additional money for this work. So to date, on top of the 5 million, we've also put in almost 2 million more, about half from our challenge grant and half from our annual appropriations. So you can see out of that challenge grant, we funded and supplemented 17 individual projects. Some of those are pilot projects that are completely covered from State, Charlotte, Chapel Hill, Duke. And then we've also done some funding out of our operating funds, which is our annual recurring appropriation. And that's another $1 million. And that's 11 projects with 8 different researchers. This is an interesting slide that I prepared back for the General Assembly upon their request back in March. So I probably need to go and update this. But we were looking as a metric for all the projects in the external funding that were directly linked to researchers on our PFAS testing network, data, pilot data that was generated that was utilized to get the additional grants, methodologies, teams, et cetera. And you can see that 2020 thus far has been a banner year, that we're almost at $15 million in external funding to our PFAS testing network members. There are a bunch of other applications in the hopper, which are indicated in 11 in yellow. So that's a pretty good return on investment. That's almost a 4-to-1 ratio, leveraging that initial $5 million from the General Assembly. Some research updates. We've had a lot of amazing people on this project, too many to note, but there's one that I've been working with specifically, and we've gotten them some extra money to move forward. And that's the Cornell Livefarth group. So they had February online publication, and then they were in the April printed version of ACS Central Science about what I call the wonder resin, but it's really their ionic Florogel. And there's still a long way to go, but early results from the lab look very promising, that this Florogel appears to be removing more PFAS compounds than other technologies out on the market right now. So we're trying to move that into the next phase. So not only did Cornell and Livefarth get the cover, they also got the editorial piece, the frontispiece, the first reactions that talked about their work, and then they got the article. And one thing I really want to note here is, you know, while this came out of the Cornell Livefarth lab, I want you to look at the order of the authors here. So Alongo was a postdoc, Irene and Leonard were grad students, and I really love to see when professors do this. We work with a lot of great professors that absolutely go to support their team and give them first billing on very ground, you know, trailblazing stuff. And I also know for a fact that they're also on the patent for this Florogel, that they have been working on protecting the intellectual protocol with the UNC patent office. So we've made sure they've gotten a little more money here, just almost $250,000. And we were in talks with the General Assembly in March, is one reason that I tendered the memo. We had support from leadership in both chambers for another large influx, monumental influx of PFAS dollars, in part for this project and in part for support for the Superfund Center at NC State and some of our other teams that were working in the air and the water components. The bill was drafted and it was getting ready to move when they came back, but the COVID hit. And of course that everybody had to pivot, refocus their policy glasses as well as the money. So that went away and got put on hold, but there is definitely still interest in the legislature. And we communicate all the time that, you know, we need a continued long-term investment to keep moving the ball down the field. Data availability update. If you go to the NC PFAS network site, which Dr. Surratt mentioned, we've got a lot of materials on there, but there's a data portal. I'm very pleased that the project management team and team 1, the water sampling team, they now have all of the reports, the analytical reports from each of the 405 raw public water supplies that we are analyzing and monitoring, and that list was given to us by DEQ. And so you can go and click and download all of those for each location. And we are in the midst of round 2. I think we're probably about halfway done. And we just are in the process of getting them some more money out the door to finish round 2. So we'll have 2 sample points for each of the 405 sites across the state. The data hub is about to go live. I'll give you a sneak peek here. This is a combo work between our risk communications team 6 and our data management team 7. We're beta testing it right now, and I logged in last night and again this morning. And that's going to be a treasure trove of data that will be available to the general public. And you may also, at some point, looking to have some type of GPS portal where you can visualize some of these data, and it may look like this. I want to underscore, this is a draft map. This is not for release. It's a prototype. It does use actual data from round 1 water sampling, but we are still working on icon size and placement and how to basically best present the categories for concentrations. But this is what we're kind of hoping to have. We're looking how to delineate iconically between groundwater and surface water samples. And that is about it on my end. Somebody's probably gonna have to stop my screen share because I cannot access the Zoom window. Thank you.
Thanks so much, Jeff. We're going to move on to a presentation from Mort Barlaz. Dr. Mort Barlaz is a professor and head of the Department of Civil Construction and Environmental Engineering at NC State University. Mort leads the NC PFAS Network's Team 5A, focused on novel PFAS inputs into the environment. And I'll let Mort take it from here.
Good morning. Can you see my screen?
We can see your screen. It looks like it's on the presenter view.
All right, let's do this. Can you see it now?
Yes.
All right. I've got a bunch of slides I'll skip, but I'll move quickly. So the focus of our thank you. First of all, thank you, and thanks for the introductory information and background. My expertise is in landfills, and in previous work, we've known that landfill leachate is a significant source of PFAS, and there was a lot of concern amongst landfill owners that all of a sudden wastewater treatment plants would say we're not going to take landfill leachate anymore, and that led to the question of, well, is landfill leachate a significant input to wastewater treatment plants? And bear with me, I had these slides hidden, but so our objective was to characterize the PFAS fingerprint of landfill leachate, and also look at the massive PFAS entering wastewater treatment plants via municipal wastewater, so that we could evaluate whether landfills were in fact a significant input to wastewater treatment plants. There are 2 flavors of landfills in this state and most other states: those that are permitted for municipal solid waste and those that are permitted for construction and demolition waste only. In North Carolina, construction and demolition waste landfills are unlined, making it challenging to collect leachate from those sites. So we got some construction and demolition waste leachate in state, and actually use some other resources to get some samples from out of state, because in other states that leachate is collected. On the wastewater treatment side, we sampled from 31 wastewater treatment plants, and those 31 plants represented about 37% of the total flow in North Carolina. So I feel like we did a good job. The results I'm going to show now are based on 10 wastewater treatment plants and 10 municipal waste landfills, and we quantified a total of 41 compounds. Any compound that you see in red, where it says either greater than 500 or number greater than the max, our detection, the upper end of our standard curves was 500. So we have any number of samples that were above 500, and we haven't been able to go back yet and dilute and reanalyze. It just means that all the numbers here are biased low. Interestingly, these two products, Naphthalon byproduct 4 and Gen X, are, excuse me, the Naphthalon byproduct 4 is proprietary to Chemours. We found it in one landfill and 2 of the wastewater treatment plants of the ones we sampled. And we found Gen X in some of the sites, in 4 landfills and 2 wastewater treatment plants. And of course, it was the PFOA substitute. Just going to point out that we also characterized our landfills, which with respect to how much leachate they produced, because what we're really interested in is mass, which is going to be the total volume of leachate multiplied by the PFAS concentration. Going to skip some of these slides and go here. So what we did is take average PFAS concentrations from the wastewater treatment plants we sampled, average PFAS concentrations from the landfills that we sampled, and then we assumed a 100-acre landfill, and the 250 GPAD is gallons per acre per day, which is the typical metric of how landfill leachate is measured. And using these numbers and then assuming a wastewater treatment plant that's 10 million gallons a day, in this table, what we looked at is for 6 select compounds, what percentage of the compound is coming from landfill leachate and what percentage is coming from domestic wastewater. Again, assuming a 100-acre landfill, a certain leachate flow rate, and we base this on a 10 million gallon a day wastewater treatment plant, which of course means if it's a 5 million gallon a day plant, these percentages would double. And if it's a 20 million gallon a day plant, these percentages would go in half. The numbers in red all represent minimal numbers because the compounds were present above our standard curve. So this 12.5 or 12.2 could be as much as a factor of 2 to 4 on the low side. But the important conclusion is that the results are going to be site specific. If we're talking about a small landfill in Wake County going to a 60 million gallon a day wastewater treatment plant, the landfill is likely a small percentage of the total PFAS entering that wastewater treatment plant. In contrast, if we're talking about a large landfill in a rural area going to a relatively small wastewater treatment plant, then the landfill leachate input is likely to be a quite significant component or quite significant fraction of the overall loading of PFAS to a wastewater treatment plant. And of course, I didn't show it here, but we're looking at PFAS concentrations in wastewater effluent as well. In general, the PFAS are not attenuated. So anything coming in is leaving the wastewater treatment plant. And we're going to divide our results across the 17 major watersheds in the state so that we can calculate PFAS loading to each of the 17 major watersheds in North Carolina. Just some observations. I just note that neither landfills nor wastewater treatment plants made PFAS. Of course, it's the things we use every day that are ending up in landfills and generating PFAS. And the reason I put that picture in the upper right, because I have a Gore-Tex dry top. And of course, it's probably releasing PFAS. So I think it's important that we recognize that there needs to be a conversation in society about what do we want? Do we want the convenience or not? And of course, the drive to safer substitute chemicals is ideal. Analysis is still ongoing, but I will share that at least qualitatively, my sense is that we're seeing comparable numbers in construction and demolition waste landfills. The big implication there is that leachate is released directly to groundwater or surface water in the absence of leachate collection. Thank you. Let me stop here and take questions when it's appropriate.
Thanks, Mort, for sharing your interesting findings, and I really appreciate your take on the observations and implications. We're now going to introduce our final speaker, Dr. Mei Sun. Mei Sun is an assistant professor of civil and environmental engineering at UNC Charlotte. Mei co-leads the NC PFAS Network's Team 3, focused on PFAS removal performance testing. Her research focus is on the occurrence and removal of emerging contaminants, and she helped reveal the presence of PFASs in drinking water sourced from the Cape Fear River. I'll let you take the speaker role, May, when you're ready.
Okay, can you hear me okay and see my slides?
I can hear you and see your slides.
Okay, great. Thank you for everyone to attend this webinar. I'm going to present our research work on PFAS removal from drinking water sources. As mentioned in the removal team, Team 3, there are multiple researchers looking at different ways of removing PFAS from water. I'm only, due to the limit of time, I'm only introducing what we are doing in our lab now. So this work is done by my postdoc, Yanling Liu, and she is also in the audience today. So the motivation of us to studying PFAS removal by ion exchange is because this is a very mature and widely used technology for treating different types of contaminants from water. And the major principle of that is to exchange the ionic contaminants with some harmless ionides in water and get the contaminants absorbed on the surface of resin. Resins are, you can think the resin as plastic beads like this, and they are specially designed to have special affinity for contaminants. And because many of the PFAS species we are looking at are negatively charged, meaning they're ionized, so they can be exchanged onto the resin surface. And based on previous literature, this treatment is more effective in removing short chain PFAS like PFBA and GNX than activated carbon. So we want to take a further look at the performance of these resins. And specifically, we are looking for answers for the following question. First, there are already plenty of study on the effectiveness of ion exchange treatment for legacy PFAS, but the study on the ether compounds that we have in North Carolina is still rare. And we want to know whether this treatment works or not for GNX and other ether compounds. And there are a few dozens, at least, different types of resins from different vendors. We want to help the utility to decide how to choose the best one. And the third question we are trying to figure out is scientifically what factors would impact the PFAS removal and resin regeneration. So with those questions, we started our test using groundwater collected from Fayetteville near the Chemours plant. We started with a screening test using a total of 9 commercially available resins. Those resins are chosen because either they have already been used in many treatment plants for other purposes. So we want to see that if this existing processes can also remove PFAS at the same time. Or like for the pure light resins, they are specially designed for PFAS. They are supposed to be very highly efficient in terms of PFAS removal. And also we tested other universal resins that have been reported effective in PFAS removal from previous studies. With all those resins, we have them in contact with the Fayetteville groundwater for different time period and we looked at a total of 40 PFAS species that includes the legacy PFCA and PFSA, which include PFOS and PFOA. And we also looked at compounds that are more related to firefighting form application, and more importantly, the ether compounds related to the Chemours chemical plant. So the compounds that are underlined are compounds that already exist in that groundwater, not surprisingly, at relatively high concentration. And other compounds are at lower concentration, so we did spike the groundwater to a 600 ppt initial concentration for each individual compound, except for the PMPA. It already exists in the groundwater over 1,000 ppt, so we didn't do any change on that concentration. And here is a quick overview of what we found in terms of percent removal of each compound by each resin. It's a very busy plot, so I'll try to explain that in details. First, the colors. The color represent percent removal. The red is not good. The blue is like good removal, and the light color is red, where removal is about half. So each column represents one PFAS compound. Each row represents one resin. So the first information we got, and also within each group of PFAS, the compounds are ordered by the length of the carbon chain or the size of the molecule. So we first found that the longer chain are better removed than the shorter chain compound. This is consistent with what people have found before. And if we take a look at the compounds that we are interested in, PFOA is removed about 50% in 15 minutes, not so good. PFOS gets better removed, all the dark blue color. And the ether compounds we are looking at, it really depends on the chain length. Since like GenX are still short chain and didn't get good removal, but this is only for 15 minutes. If we leave the resin in the water for a longer period of time, 24 hours, for example, well, the good news is you now see a lot more blue, meaning we are able to remove a lot more PFAS. And now if we look at PFOA, it gets removed well. PFOS, almost complete removal. And for the ether compounds, well, most of them get removed pretty well, especially in this group of resins. And you see the difference among different resin groups. The resins are grouped by the matrix of polymers. So you also get the first impression from this plot that the different matrix, polymer matrix, does have an impact on the performance. So if we take a closer look at the polymers that are used to make the resins, the PS-DVB resins are performing very well. They are able to remove 83% of the 40 compounds in 24 hours with greater than 90% removal, while the other two resin types did not do a job that is as well. So having found that this group of resin, a total of 5 within the 9 we tested, are performing pretty well, we proceed to the next step of our research, looking at only those 5 resins. We did kinetic tests. So we still use those 5 resins. We take samples more often to look at how fast the PFAS can be removed by those 5 resins. And we still use the same 40 compound mixture, but we also increased their initial concentration a little bit so that we can see the concentration change better. But this 1,000 ppt is still very relevant to our drinking water treatment in North Carolina. And basically what we found are curves like this. The resins are continuously uptaking PFAS, and the speed of PFAS uptake across different groups, across different chain lengths of the compounds does not differ that much. Those curves are more or less in parallel. And that means the PFAS compound properties does not affect the removal rate as much. It does affect the amount removed a lot, but not the rate. But if we also look at different structures of the resin, even with the same polymer type, whether the resins are in gel type or in micropores does have an impact on how fast they can remove PFAS. So with those 4 illustrations, they all tell us that the gel type resins can remove PFAS faster, but in the end, the total amount of PFAS removed by different resins are similar, not that different. So that's the key conclusions from our kinetic test. And in the end, we looked at regeneration. So those resins, except for the 2 PFAS specific resins, are not supposed to be disposable. In traditional water treatment for other contaminants, the resins are supposed to be able to be regenerated, restore their removal capacity, and be used in the next cycle. That's the only way to make this treatment affordable. So we want to look at if there is any way that we can regenerate the resins in a practical method. So in previous literature, people found that if you use 70% methanol to regenerate the resin, you do resume the capacity, but the 70% methanol is really hard to handle in real life in the treatment scales. Treatment plant scales. So we want to see if simple salts could do the regeneration work, or a low percentage of solvent could do the work. So we still looked at only the top 5 resins with the PS-DVB matrix, same spiked groundwater, and we looked at different salt composition, different salt concentration, different pH, and we ended up still adding a little bit of methanol, trying to see if a low percent methanol could do the work. And due to the time limit, I'm only going to show you the results as an example for the concentration of the salts. So you can see that with all those 5 resins, increasing the concentration of the salt does help improve the regeneration of recovery of different PFASs. So in those plots, each dot represents the recovery of 1 PFAS compounds. And you can see a few things from here. First, the recovery across different compounds varies a lot. You see dots up to 80% recovery. You see dots that are not recovered at all. So that's what the compound property decides percent recovery. And also you will see that for every resin, using a higher concentration of the salt improves the recovery from essentially no recovery at all to about 25% a quarter recovery. And also if we have to rank the ease of regeneration within those 5 resins, the ARA 910 is the one that can be recovered most. While those 2 PFAS specific resins, although they are great in terms of removing PFAS from water, it's really hard to recover that. So as the manufacturer said, this resins should be disposed after 1 use instead of trying to be regenerated. While the other 2 universal resins, their recovery are in the middle. And also, as I mentioned, we also tested other factors. We concluded that chloride salt works better than bicarbonate salt or acetate salt as the regenerant. Meanwhile, the chytine type pH doesn't really help, doesn't really matter. And if we add methanol to 10%, 20%, it has very limited enhancement on regeneration. If we want to get over 50% removal on average, we seem to only have the option of using a much higher organic solvent content to do the work. So finally, the take-home message from our study so far is that the PS-DVB resin is the best among all the 3 polymer types that we surveyed, and they are capable of removing above 90% of the 40 compounds that we tested within 24 hours. In terms of the rate of PFAS removal, the gel type works better than the microporous type. And it is pretty, one thing I didn't have time to show the data for is that we did observe desorption of some PFAS in some resins that some of the PFAS was initially uptaken by the resin, but leaving the resin in the water for a longer period of time, some compounds come back to water. So that is the bad news. However, this does not really occur much for the 5 resins we focused on studying. Long chain compounds are removed better than the short chain compounds, and regeneration is difficult. Increasing the brine concentration helps, but the other efforts that we tried did not really give us much improvement. So in the end, we can remove PFAS using air exchange resins. The key challenge right now is what to do with the resins afterwards. And we are working on that right now. So that is the major information I want to pass for today's webinar. And if I'm happy to answer questions towards the end. And if there are more information that you want to dig into, please feel free to contact me with that email address in the bottom of the page. Thank you.
Thank you so much, May, for sharing your interesting research. I misspoke previously. We have one more very important presenter, Dana Sargent. Dana Sargent is the Executive Director at Cape Fear River Watch, and we are excited to have Dana present today to share the community perspective on this topic. I'll let you take it away, Dana.
Thank you. Can you hear me?
Yes, I can hear you, and we can see your slides.
Perfect. And so I'm going to talk I have 5 minutes here. I thought the best use of everyone's time for my part, was to give you a quick update on the consent order, and then I'll provide my thoughts on community right at the end. So what is the consent order? The consent order was the result of a couple lawsuits filed by Cape Fear River Watch against both Chemours and the DEQ through our counsel at the Southern Environmental Law Center. All 3 parties agreed to the terms detailed in the order, and it was signed February 25th, 2019. So what does it do? It does a lot. I'm going to try to summarize here, but overall, it requires Chemours to stop its decades-long discharge of toxic pollution and clean up the site. It does this through required reductions in air emissions, groundwater, and surface water discharges into the Cape Fear River. It also provides relief to those with contaminated drinking water wells around the Fayetteville Works facility via water replacement supplies and systems. It also requires health toxicity studies on 5 prevalent PFAS found in the wells surrounding the facility, and leaves open the possibility for further tox studies. It requires long-term sampling of soil, water, and air, and includes non-targeted analysis of process and non-processed wastewater and stormwater, as well as total organic fluorine reporting. Cape Fear River Watch, along with our counsel at Southern Environmental Law Center and the amazing work contractors that they've hired and experts, are active parties to the order, and we are holding Chemours' feet to the fire to make sure that they are abiding by its requirements. Progress so far. As most of you know, the processed wastewater continues to be captured and shipped off-site for disposal. We know there's issues with disposal, but that's what's happening to it right now. Air emissions, you heard about earlier, that's a photo again of the thermal oxidizer. It was up and running by December 31st, 2019, and it continues to control process emissions at an average of PFAS destruction efficiency exceeding 99.99%. Old Outfall 2, I'll get a little bit more into this on the next slide, but the technology was in place October 1st, and we expect this to eliminate about 1/4 of the PFAS leaving the site into the Cape Fear River. Non-target analysis, the first report was released June 30th. It was pretty shocking. They found quite a number of PFAS that we hadn't really known were there yet. Tox studies are about to start phase 1 of their testing schedule. And well sampling and water replacement updates. Sampling is going to be ongoing around the site of personal wells until PFAS is non-detectable. As of June 30, there are 2,293 residents receiving bottled water. 750 homes have reverse osmosis systems installed, and 82 homes have granular activated carbon systems online. So the permit issued at Old Outfall 2, you can see a sort of picture of it there, was issued by DEQ September 18th. This is for a water treatment system on site to remove PFAS from a contaminated stream that currently flows into the river. The consent order required this to be operational by September 30th. It's operating today. The system must remove at least 99% of PFAS from the stream, thereby reducing by about a quarter the load impacting downstream communities. And Cape River Watch voiced concern in our comments to the permit about the effluent limits and that they should be based on levels achievable with current technology. So DEQ has agreed to revisit the system in 3 years to determine if the technology has proven that Chemours can do better. The addendum, some of you may have heard this, it went out for public comment. What that is at the time the consent order was written, obviously we didn't have all the information yet about the pollution at the site and the pathways of it. So paragraph 12 was written in to outline a process by which Chemours was required to use the data that they were required to gather from February 2019 to inform this proposal. After reviewing public comments, DEQ has filed the proposed addendum for entry by the Bladen County Superior Court. That hearing is going to be held this coming Monday. The requirements under the addendum will address pollution coming from 3 major sources, including groundwater, seeps, and stormwater. By spring 2023, it requires the company build an approximately 8,000-foot underground barrier wall to capture and treat contaminated groundwater. It requires Chemours to promptly begin installing filters in its seeps. And this is a picture over here that I took from one of our site visits. That's kind of what a seep looks like. That's what they call a seep. It looks like a little stream, basically, highly contaminated, flowing into the river. These filters will immediately remove 80% of the PFAS, and then following completion of the barrier wall, the filters will reduce PFAS from the seeps by at least 99%. And finally, the addendum requires the company to capture stormwater or runoff from the most contaminated portion of the site and remove at least 99% of the PFAS. So in summary, the proposed addendum requires 99% removal of PFAS from all of the most significant remaining sources of pollution entering the Cape Fear River. So barring any unfortunate interventions, all of this important work will be approved by the court this Monday, and Chemours will get going on it. Putting on my policy and communications hat real quickly, I want to say thank you to the scientists of the PFAS network. It's really difficult to follow the amazing May Sun, but I do need to say that myself and Cape River Watch as well agree that obviously we need more science. People are sick, people have died, and we need to know why, and we need to understand the health outcomes. We need to understand how to get rid of this stuff, but we believe that the regulatory bodies have the authority and need to use the authority to stop these polluters from further exposing our environment and our population to these chemicals. So this website here is the consent order compliance website, which was required by the order, and Chemours is required to update this site regularly with all of their information, data, and updates relative to the consent order. So I encourage you to check that out for more information. Thank you so much.
Thank you so much, Dana. What a great presentation. So it looks like we have just a few minutes for our Q&A session. I'd like to note that we also have Dr. Sue Fenton. She has joined to help us in answering questions as well as the presenters and panelists. Sue is the leader of the reproductive endocrinology group at NIEHS. Please, if you have any questions, type them into the Q&A box so that we can get those answered. We did have a question come in right after Mort's presentation, so I'm assuming it's for him. The question was wondering whether the full set of data will be available.
Well, it'll be available as soon as we have it, where the analytical work isn't complete. But of course, as soon as we have it, it will be available. The actual site locations are blinded, but the region, Piedmont, Mountain, Coast will be identified, and of course we'll be looking at discharge to the various watersheds.
Great. And I'll also note that some of the presenters are able to stay on for about 15 minutes longer to allow time for additional questions, but we understand if any of the attendees have to jump off at 11. A question for Dana. Have Chemours started their tox studies yet?
So yeah, they had, they're working on 5 PFAS, and they're about to start phase 1. And phase 1 includes analytical method development and initial studies that are necessary to set the dose levels. So that's where they sit with those.
Great. Question for May. What happens to the brine salts after regeneration of the resins?
Yeah, this is a great question. So once we regenerate resins, we use a smaller volume of brine to regenerate the resin comparing to the volume of water, drinking water to be treated. So that's actually a concentration process. And once we have a smaller volume to deal with and a higher concentration to deal with, we can use the more harsh and expensive treatment, destructive treatments. Like my lab is working on electrochemical degradation. One of my collaborators out of those, the North Carolina, is working on chemical treatment. There are also other types like photochemical treatment or plasma treatment that can convert PFAS into inorganic fluoride, but they are too expensive to be used for drinking water directly.
Thank you. All right, we'll wait for some more questions to come in. I understand if people have to jump off the seminar, but we thank you so much for participating and for engaging in this issue. We're very pleased with the presentations today and the turnout. Oh, we have another question for May. How are the resins introduced into the water, and do they have any impact on the environment?
Well, we don't introduce the resins to water. We introduce water to the resins. So in the treatment plant, they would build a unit where they pump water through the resin. The resin would be packed into a column and water would flow through it. And I don't really understand the question of what the impact on the environment is. If the audience could specify what that means.
I'll wait for them to specify. They're typing, so it might take a second. Let's see. Would the resins be harmful to the environment? Does that help clarify?
Oh, sure. So it depends on how they manufacture the resin. So I am not the expert of manufacturing, so I do not know for sure. What I can say for sure is those resins we have been testing are not fluorine based, so at least they are not releasing PFAS when they are being manufactured.
Great. Another question for May. This question's from Emily Sutton. She said that your presentation was exciting and encouraging, and she knows she's mentioned this to you before, but she wants to stress the concern that these removal technologies be used at the discharge location rather than at drinking water intakes, whether that is wastewater treatment plants or individual discharges and pre-treatment users. Before, you had mentioned that the organic matter in the wastewater treatment plants make it difficult to be as effective in the long term. How would you recommend utilizing these resins to remove these compounds from the source?
So using resins to remove PFAS from the source might be less affected by the organic matter comparing to using activated carbon, because the resins are just not as sensitive than the carbon. So if we are talking about an industrial waste source like the chemical plant, I think the resins actually would have the potential to work. And so yes, I think it's worth digging into the treatment of PFAS at the source using resins. And I believe I've seen research doing so, using the resins to treat a much higher initial concentration.
All right, a question, I think this one's for Mort. Were landfills the only sources to wastewater plants assessed? Are there other industry types considered or being considered?
So leachate was the only source that was quantitatively assessed. We did ask what other wastewater, what if there were industrial wastewater discharges to a given wastewater treatment plant, and we recorded that information. We did not sample those individual streams. In some cases, it would not have been, we would have had to go to the industry itself. And in other cases, it might come in by tank truck. That was A, beyond our scope, and B, there was some pushback in some cases. And there were some plants that, some wastewater treatment plants that received wastewater from sources we were highly suspicious of, and they weren't interested in our sampling their facility. So the question is right on. It is unfortunately beyond our scope to have analyzed every input to wastewater treatment plants, but entirely appropriate based on, for specific plants where we see elevated levels, it's entirely appropriate to do that. Probably the best thing is when our data set is complete, we'll be able to look at which plants received some industrial wastewater and which did not. And let's look statistically and see if they're higher, or if there's some signature compound that leads us to suspect there's an industrial source.
Great. Let's see. Were any military installations considered during sampling?
In the case of landfills and wastewater treatment plants, during sampling, they were not.
Okay, and then how do you take care of the PFAS-laden resin so that PFAS is not reintroduced into the environment? This question's for May. And can you degrade the PFAS in the resins and regenerate the resins at the same time for future usage?
This is again a great question. I have a pending project on exactly that topic to look into methods that would be able to regenerate and destruct the PFAS on the resin at the same time, but we don't know yet.
Can I make a comment on that as well, Megan?
Definitely.
Yeah, Mort, Barlaz, again, right now, at least some spent resin, whether it's activated carbon or ion exchange, is quite likely going to landfills. And it begs the exact question that's being asked of, if I put a PFAS contaminated resin into a landfill, A, do PFAS leach off of it or not? And if they do, is that resulted in appreciable change in the landfill leachate PFAS concentration? And like May, I have a proposal pending to look at that, but it's an open question. We don't have reliable leach tests that are landfill relevant, and we don't have a body of experimental data to answer that question, but many of us are asking that question.
Thanks, Mort. Let's see. Were airports or firefighting training facilities considered as PFAS sources for sampling?
No, since that would be a surface water contamination issue or a groundwater contamination issue. It wasn't our focus because we were looking at what was going into wastewater treatment plants, but from everything I've seen, there's not much question but that would be heavily contaminated water. So I'm not really sure what's behind that question in terms of what missing information we would come up with there, given that they're known sources.
Mm-hmm.
This is Jason. I just wanted to add, we definitely have, for some of the water sampling sites and also a couple of our air sampling sites, we're not too far from airports, but we weren't directly on properties or close on the properties of these facilities to say for certain, but we have sites that are not too far away.
Great. Let's finish with one question that's directed towards all panelists. What do the panelists think are the most promising removal technologies at this point?
From Cape River Watch's perspective, we should be stopping this stuff at the source. Understanding we have to remove what's existing. So I am not a chemist, and I will obviously let the smart folks in the room answer that question, but I do think we need to continue to press the polluters to stop the discharge. We're just going to keep going around and around.
This is Mort, and you know, others are more expert on treatment technologies. I would only say that it's an open question in the short term, and I don't doubt 1, 2, 3 years from now, whether it's the work that May is doing or the work that Jeff described in the Cornell lab, that will be in a lot better shape in a few years. There's a question I see about GAC regeneration. And again, there's papers coming out on how effective that thermal activation step is at actually destroying PFAS. So my sense is that there's a lot of attention being given to these issues, and that there's a lot of parallel technologies being developed in parallel. And everybody that I talk to is very sensitive about, you know, let's not solve a problem in one ecosystem or environment and just transfer it to another. So the question is understood. I don't know that there's a perfect answer yet.
This is May. Yes, I agree that right now we don't have the perfect answer yet. And yes, it is a very big concern that whether we are transferring the contaminants from one medium to another. So in terms of what is the best treatment technology so far, I think it is still, we still need a treatment train, like we first do a PFAS concentration to enrich the PFAS into a smaller volume and then do chemical destruction. We do need to break down the molecules to make sure that they don't go to another compartment and then eventually come back to the environment.
Any last comments for that question? We are well over time, so I want to wrap it up if there's no other comments.
This is Gary. I'll throw out 2 quick comments here. So on the air side of things, we also have concerns about what happens in terms of regeneration of activated carbon that's being used to control air emissions. I mean, we have some familiarity with how some of the activated carbon companies do their regeneration, and most of them end up having a RCRA qualified thermal oxidizer on them, but you know, they're actually more generally applied for a broad range of organics and not just the PFAS. So there's some concern over that regeneration step. I know that also for fairly pure streams of PFAS, there's a look at how to recover some of those PFAS directly from the carbon and reuse that. But there's a lot of work left to be done. And finally, on the thermal oxidizer stage, which is where, you know, we've landed in terms of the Chemours facility down there in Fayetteville. You know, it's not your standard thermal oxidizer in terms of the way all the thermal oxidizers I've ever looked at in the 40-some years I've worked on air pollution issues. It really is another chemical process of operation. So you really do have to reduce the emissions at the source, minimize them and use controls there. The thing that's interesting about that particular system is it actually is designed to take the fluorine, to break down the compounds and take it back to HF and really put it back into a material, which is where the fluorine started from to begin with, which is calcium fluoride. So that's my 2 cents worth there.
Great. Thanks to all of the presenters and for all of the attendees for sticking around for an extra 15 minutes. We'll go ahead and finish this webinar now, and we hope to see everyone at our next webinar on October 23rd. Thank you so much.
Thank you.
And thank you, everyone.